You know, usually when we talk about like a software stack or a diagnostic process, there's this expectation of mechanical precision.
Right.
I
Yeah.
mean, you break your arm, the x-ray shows a jagged white line on a black background, and the doctor just points to it and says, there it is.
Yeah, the fracture is right there. It's categorized, and the solution is a cast.
Exactly. Or, well, you get a bug in your code, the stack trace points to a null pointer exception on like line 42,
Yeah,
and you just fix the syntax.
this is very binary.
It is. And we've built the entire discipline of software engineering and, by extension, data science around these very comforting discrete layers.
Oh, we absolutely love our boundaries. I mean, the von Neumann architecture practically trained us to think in those neat little boxes, right?
Yeah, processing here, memory there, user input over there.
Exactly. It makes debugging actually possible.
But, well, if you look at the research and the code shipping during the week of June 29 to July 5, 2026, you realize that X-ray machine is, it's fundamentally broken.
Completely broken.
The clean lines between those layers are just dissolving. We are looking at a technological landscape right now that is incredibly murky, but I mean in the most exciting way possible.
It really is. We're seeing hardware that operates, well, almost like biological tissue.
Yeah, and memory systems that act like these decoupled conceptual shadows.
Right, and interfaces that just bypass the physical keyboard entirely, to read human intent straight from the cortex.
Which is wild. It's the absolute definition of diagnostic muddy waters.
It is. The foundational architectural shifts happening right now just completely defy the traditional categories we've relied on for decades.
Yeah, the entire stack is being compressed, intertwined, and in some cases just completely reimagined from the ground up.
And that is exactly why we are here today.
Welcome to the deep dive. If you are a data scientist, a machine learning engineer, or just someone who really needs to cut through the relentless marketing hype of parameter counts and benchmark scores, you are in the right place.
We have a massive stack of sources from this single week to go through.
We really do. Research papers, corporate blogs, technical teardowns, and our mission today is to extract the actual signal for you.
Right. We're going to unpack some really complex new paradigms, things like brain-to-QWERTY, SkillOpt, Memora, Mancar, and phase-change neuromorphic chips.
And more importantly, we are going to figure out the underlying mechanics of why they work and how they will actually impact the models you build tomorrow.
Because to set the analytical stage here, it's really crucial to understand what that signal actually is.
Yeah, the industry has spent, the last few years obsessed with raw scale.
Oh, absolutely. The race to 1 trillion, 2 trillion parameters. Brute force.
Right. But the real narrative in our sources this week isn't about brute forcing intelligence with size.
No, it's entirely about efficiency and representation. It's about how models remember context dynamically, how they mathematically constrain their own reasoning, how they, algorithmically self-evolve their skills.
And crucially, how they execute on entirely novel silicon topologies.
Exactly.
Okay, let's unpack this. I feel like the only logical place to start is at the absolute bottom of the stack, the physical layer.
Because all the algorithmic magic we're going to talk about today doesn't just exist in a vacuum.
Right, it requires a physical substrate. And right now, the von Neumann architecture, which, as you mentioned, separates where data is stored from where it is processed, that has become the ultimate bottleneck in modern machine learning.
It really is the wall we keep hitting.
Every single time an NVIDIA GPU wants to multiply a matrix, it has to fetch the weights from high bandwidth memory, ferry them across a physical bus to the processing cores, do the math, and send the result back.
And the energy cost of moving that data is frankly orders of magnitude higher than the energy cost of the actual computation.
It's an incredible waste.
It's a massive waste of time, power, and thermal budget. I mean, you are constantly fighting the speed of light and electrical resistance just to shuffle numbers around a board.
Which brings us to a really massive breakthrough highlighted in our sources this week.
Yes, the Peking University paper.
Right. A joint team from Peking University and the Chinese Academy of Sciences, or CAS, has developed the world's first millisecond-level neurodynamic system chip.
And the architecture here is just wild.
It is. They aren't using traditional silicon transistors at all. They are using phase-change memristors.
And the benchmark they published is what really turns heads. They claim this chip is 50 to 478 times faster than an NVIDIA A100 for brain modeling tasks.
Wait, 478 times faster?
Yeah. But to understand why that specific number matters to you as a data scientist, we really need to dive into the physical mechanics of a phase change memristor.
Let's do it.
Okay, so a traditional CMOS transistor is essentially a microscopic on-off switch.
Right. It routes current to represent a 1 or a 0.
Exactly. But it requires constant power to maintain that state, and, well, it doesn't actually store the data itself.
Hmm.
A memory resistor does exactly what the name implies.
It remembers.
Yes, it remembers its electrical resistance state even after you cut the power.
So it's basically mirroring a biological synapse.
Precisely. In the human brain, a synapse physically changes. It strengthens or weakens based on the frequency and intensity of the signals passing through it.
Long-term potentiation.
Right. And a memristor is doing that physically in hardware. In the Peking University and CAS chip, they use these phase change materials, which are typically chalcogenide glasses.
The physics of chalcogenide glass are so fascinating here.
They really are. When you apply a specific, precisely timed electrical pulse, you actually heat the material up and change its atomic structure.
Oh, wow.
Yeah, you can force it into an amorphous, highly disorganized state, which has very high electrical resistance.
Okay.
Or, with a different pulse profile, you can crystallize it into a highly ordered state with low resistance. And importantly, you could hit all these analog states in between.
So you have analog non-volatile memory.
Exactly.
So the data isn't being stored as some tiny magnetic charge in a separate bank of RAM. The data, the actual weight of your neural network, is the physical atomic state of the resistor itself.
And this is exactly where the von Neumann bottleneck just shatters.
Because you aren't moving the data.
Right. Because the resistance value of the material represents your network weight. You don't need to fetch it. You simply pass a voltage through the memristor array.
And according to Ohm's law, voltage equals current times resistance.
Yes. So the resulting current that flows out is mathematically equivalent to the multiplication of your input, the voltage, and your weight, the resistance.
That is so elegant.
It is. The physics of the material naturally perform the matrix multiplication in place. You are computing literally inside the memory cell.
Okay, hold on, though. I have to look somewhat critically at that 478x speedup over an A100.
Fair enough.
Because that sounds incredible on a press release, but,
They will.
well, as developers, we know that benchmarks can be highly curated.
Oh, for sure.
If traditional GPUs are like a massive, highly organized accounting department, workers meticulously fetching ledgers, executing high-precision floating point math, and putting the ledgers back, are these neuromorphic chips more like a biological reflex?
That's a really good analogy.
Like super fast, deeply ingrained, but maybe fundamentally incapable of the high-precision backpropagation needed to train a foundation model.
That distinction is absolutely vital here. Historically, neuromorphic chips have been pigeonholed into very specific, noisy, low-precision inference tasks.
Right, like vision sensors or audio wake-word detection.
Basically reflexes, yeah. The analog nature of a memristor means you just don't get pristine 64-bit floating point precision. You get noise, you get temperature drift, read-write variations.
So you definitely cannot use this to train a trillion parameter transformer from scratch using standard gradient descent.
Oh, the accounting department is still very much required for that.
Okay, so what makes this new Peking University chip different from all the neuromorphic experiments we saw like 5 years ago?
The real breakthrough is hidden in the phrase millisecond-level neurodynamic system. They've actually engineered the phase change dynamics to operate on the exact timescales necessary for complex temporal sequence modeling. Traditional memristors either flip states way too fast or way too slow to accurately model the temporal dynamics of biological neurons, like in spiking neural networks.
So they couldn't hold a complex rhythm.
Exactly. But by turning the chalcogenide alloy, they've aligned the hardware's physical relaxation time with the temporal features of complex data streams.
Oh, that's brilliant.
It's capable of sustained dynamic state changes that actually mirror complex brain functions, specifically for tasks that require real-time processing of continuous, messy, temporal data.
So for the listener who's sitting there deciding what hardware backend to target next year, this changes the calculus entirely for edge deployment.
It changes everything for the edge.
Imagine deploying a continuously learning, highly capable anomaly detection model on a satellite or like an internal medical wearable. You just don't have the power budget for a GPU out there.
Not even close.
But if the model is running on a fraction of a milliwatt because it's processing information natively in analog memory, that fundamentally changes where we can physically locate intelligence.
Absolutely. And while Peking University is completely rethinking the physical substrate, we also really have to look at how the rest of the industry is trying to save the traditional silicon paradigm.
Right, because silicon isn't giving up without a fight.
Exactly. Huawei's chief architect, He Tingbo, just published the Tao's Law V2 paper, and it details this incredible process called LogicFolding.
And the headline claimed there is a 53.5% boost in Kirin transistor density, which paves the way for CPU frequencies exceeding 4 gigahertz.
Which is massive when you consider the context here, the agonizing death of Moore's law.
Yeah, we have been suffocating against the hard physical limits of extreme ultraviolet or EUV lithography for a while now.
We were building transistors so ridiculously small that we're dealing with quantum tunneling.
Right, you shrink the insulating barrier too much and the electrons just sort of teleport across the gap.
Yeah, they just ignore the barrier. The
Yeah.
traditional 2D planar shrink is dead.
The industry moved to 3D transistors years ago with FinFET, right? And more recently, gate-all-around architectures to try and control that electron leakage by wrapping the gate around the channel.
But LogicFolding, as detailed in this Tao's Law V2 paper, represents a massive leap in architectural topology. It goes way beyond just changing the shape of the transistor.
So what are they doing?
It's about intricately intertwining the logic gates themselves across 3 dimensions to minimize the physical distance a signal actually has to travel.
So it's basically like playing 3D Tetris with standard cells.
That is a great way to visualize it.
Yeah.
In a standard chip layout, you have a massive problem with RC delay, resistance capacitance delay.
Because of the microscopic copper wires connecting everything.
Right. Those wires create parasitic capacitance and resistance, which slows down the signal and generates a ton of heat. By folding the logic blocks, Huawei is drastically shortening those interconnects.
And shorter wires mean less resistance, less capacitance.
Lower power consumption, and ultimately much higher clock speeds.
But okay, the immediate engineering question that comes to mind for me is thermal density.
Oh, heat. Yeah.
Because if you pack logic gates 53.5% closer together by literally folding them over each other, you are creating a concentrated microfurnace. How on earth do they dissipate the heat? Because if you can't cool it, you definitely can't clock it to 4 gigahertz.
No, it would just melt. The Tao's Law V2 paper actually addresses this through some highly advanced power delivery networks and thermal routing techniques that are integrated directly into the folded structure.
Oh, so it's built-in cooling.
Basically, yeah. They are essentially building microscopic heat pipes and power rails that run vertically through the folded logic, and they pull heat away from the active silicon down to the substrate way faster than traditional lateral routing.
It's a holistic redesign of standard cell libraries, then.
Completely.
The broader takeaway here, I think, is that the era of lazy hardware scaling is officially over.
It is entirely over.
You can't just wait 2 years for TSMC to shrink the node from 3 nanometers to 2 nanometers and expect to get a free 15% performance boost anymore.
You really have to optimize.
Whether it's shifting to phase change neuromorphic memristors for edge inference, or utilizing ultra-dense folded logic for core compute, you're going to have to be deeply aware of the specific silicon topologies your models are being deployed on.
The hardware is just no longer abstracted away. Hardware dictates capability.
It does.
And with these physical bottlenecks being aggressively addressed, our immediate next bottleneck becomes context.
Ah, yes. Context windows.
Because if we have the hardware speed, how does the model actually hold and retrieve the complex memory required to use that speed effectively?
And that transition is perfect because anyone who has built a complex AI agent pipeline recently knows the absolute agony of managing context windows.
It is painful.
You build a retrieval augmented generation or RAG system, you have a long, nuanced interaction with the agent, and eventually, well, it just drops the thread.
It forgets a key constraint you established an hour ago.
Exactly. Or, alternatively, you use one of these massive 2 million token context window models, and every single time you send a new message, you are paying the massive compute cost to reload and reprocess the entire history of the conversation through the attention mechanism.
The quadratic scaling problem of the transformer architecture is inescapable here.
Right, the computational cost of the attention mechanism grows exponentially with the length of the sequence.
But Microsoft Research just introduced a potential paradigm shift to solve this. It's a system called Memora.
Which they describe as a harmonic memory representation, right?
Yes, and it's designed specifically to give agents long-term cohesive memory by completely separating what is stored from how it is retrieved.
Okay, to appreciate how radical this is, we probably have to look at how a standard RAG pipeline operates today.
Definitely. So currently you take a document, you chunk it into arbitrary, say, 500-word blocks.
Right.
You run those blocks through an embedding model to create dense vectors, and you store them in a vector database.
Yeah.
When a user asks a question, you embed the query, do a cosine similarity search, grab the top 5 text chunks that mathematically align with the query vector, and you just shove that raw text back into the prompt.
So the retrieval mechanism is inextricably linked to the raw, literal text chunks.
Yes, and it's highly rigid.
Very rigid.
If the context of a concept spans across 20 different chunks, standard reg struggles to synthesize it, or it just bloats your prompt with useless filler text attached to those chunks.
But Memora breaks that linkage entirely.
It does. It introduces a dynamic, abstracted representation layer, the harmonic memory.
So mechanically, if I'm a developer building this today, am I still chunking text?
You are, but instead of just embedding raw text, Memora builds a structured, abstract graph of the concepts within the context.
Oh, like a knowledge graph.
Yes, exactly. Think of it as a hierarchical knowledge network, where nodes represent abstract ideas, entities, and relationships, and the edges represent temporal or causal links.
Yeah.
This is the harmonic representation.
Okay.
So when the agent needs information, it doesn't do a brute force similarity search against raw text. It queries this abstracted lightweight graph layer first.
So it's like a vast library where the index system is entirely decoupled from the physical books.
That's it, exactly.
The agent can dynamically reorganize the map of the library, draw new conceptual connections between subjects, and update the catalog based on new conversations, all without actually having to move a single heavy physical book off a shelf.
And that analogy really hits the core of the time complexity savings here. By querying the abstract representation first, the agent understands the broad flow of, say, a month-long project. Yeah. Only when it identifies the precise abstract node that contains the required detail does it zoom in and retrieve the specific high-resolution raw data associated with that node.
It perfectly balances abstraction with specificity.
It really does.
For a developer, this changes the architecture of autonomous agents completely. You can maintain a near-infinite episodic memory of a user's preferences, project histories, coding styles, without blowing up your token costs or latency on every turn of the conversation.
Because the agent remembers the shape of the knowledge and only retrieves the substance when strictly necessary.
Which naturally leads to the next algorithmic challenge. Once Memora retrieves the correct specific memory, the agent has to reason over it.
It has to actually generate a response or an action that makes sense.
Right. Which brings us to one of the most mathematically intriguing papers published this week, MANCAR.
Yes, developed by Fukong's team and Xiamen University.
MANCAR stands for Manifold Constrained Adaptive Reasoning, and it's applied specifically to generative recommendation systems. And the headline here is just wild. They achieved a massive 46.88% improvement in NDCG at 10.
Which is normalized discounted cumulative gain at rank 10. It is a metric used to evaluate the quality of a ranking system, measuring not just if the relevant items are in the top 10, but how high up they are.
Okay, hold on. I have to step in on that metric.
I thought you might.
Because anyone who works in e-commerce or content recommendation knows that mature systems fight for months, running massive A/B tests to eke out a 0.5% or 1% gain in NDCG.
It's a bloodbath for fractions of a percent.
Exactly. You're talking about algorithms deciding what billion-dollar product to show a user next. A 46% jump is frankly absurd. That number is so high it sets off immediate alarm bells for me.
Right.
My first thought is that this isn't a generalizable breakthrough at all. It's a model that hideously overfit to a pristine, highly sanitized data set.
And your skepticism is entirely warranted here. A jump that large almost always indicates that the benchmark data set had a highly pronounced structure that just perfectly aligned with the algorithm's assumptions, whereas, real-world data is infinitely noisier.
Right.
However, if we look past the sensational benchmark number and examine the underlying mathematics of MANCAR, the concept itself is undeniably a major step forward for generative recommenders.
So what exactly is the math here? What is a manifold constraint in this context?
To grasp this, you really have to visualize the high-dimensional latent space that generative models operate in.
Okay.
When a model is trying to generate a recommendation, it's navigating a mathematical space of hundreds or thousands of dimensions. The problem is that this space is not a dense, meaningful continuum. It is mostly just vast, empty, mathematically valid, but logically meaningless void.
Right. If you let a generative model freely output a vector anywhere in that space, it will hallucinate.
Oh, constantly.
It will find a mathematical coordinate that technically satisfies an equation, but translates to suggesting a user who loves obscure French cinema and knitting would be highly interested in purchasing a commercial deep fryer.
Exactly. It might make sense in the wild dimensions of the latent space, but not in human reality.
So how does MANCAR fix that?
Well, it used the manifold hypothesis. This suggests that real-world, valid, high-dimensional data actually lies on or near a much lower dimensional topological surface embedded within that massive space. That surface is the manifold. Think of a 2D sheet of paper crumpled up and suspended in the middle of the 3D room.
I like that.
The room is the latent space. The paper is the manifold.
So valid user-item relationships only exist on the surface of the paper. Everything else in the room is a hallucination.
Precisely. So what ManCard does is introduce a mathematical constraint during the reasoning process itself.
Oh, I see.
Instead of allowing the generative model to step freely through the high-dimensional void during its adaptive reasoning steps. ManCard calculates the local geometry of the manifold based on the training data, and it physically mathematically restricts the model's trajectory to stay on the surface of that crumpled paper.
It adds topological guardrails to the reasoning engine.
Exactly. It forces the generation process to respect the underlying geometric topology of actual human behavior, rather than just relying on unconstrained vector algebra.
That makes so much sense.
Even if that 46% benchmark degrades significantly on messy, sparse, real-world data where the manifold might be fractured or hard to map, the architectural shift is profound. We're moving from hoping the model guesses right in the void to mathematically shackling it to reality.
I love the mechanics of that. So, okay, let's look at where we are. We've solved the physical bottleneck with neuromorphic and folded chips. We've decoupled memory retrieval with Memora, and we've constrained the reasoning space with ManCar.
We are building an incredibly capable, efficient brain.
But how do we actually teach this brain to do specific tasks? How do we program complex workflows without breaking it?
And this is the core challenge of the agentic evolution. We are transitioning from passive models that simply answer questions to active agents that execute multi-step workflows.
Right.
And historically, the tools for teaching a model a new skill have been incredibly flawed.
You essentially have two bad options. Option one, you fine-tune the model.
Which is painful.
Very. You take your base weights and run thousands of examples of SQL queries through it with gradient descent. The problem is fine-tuning is computationally expensive, and it constantly runs into the catastrophic forgetting problem.
Yeah, you fine-tune it so hard on SQL that it suddenly loses its ability to summarize legal documents.
Exactly. Its internal representations get overwritten.
And the alternative is option 2. Prompt engineering. You write a massive, fragile system prompt. You are an expert SQL developer.
Yeah.
Always use inner joins unless specified. Never drop a table.
Yeah.
You append this to every single interaction.
But prompt engineering is more alchemy than computer science.
It really is.
You change one word or add a comma, and the model's behavior shifts unpredictably. It's nearly impossible to optimize systematically.
But this week, Microsoft Research published a paper that completely bridges the gap between those two flawed approaches.
SkillOpt.
Yes. And the subtitle of the paper explains the entire paradigm shift. Agent skills as trainable parameters.
Which is such an elegant solution. It turns the messy alchemy of prompt engineering into a rigorous mathematical training process, but it does so without altering a single neural network weight inside the base model.
Exactly. But how do you do gradient descent on a text prompt?
Right, because text tokens are discrete. You can't take a partial derivative of the word banana.
No, you can't.
Yeah.
Gradient descent requires a continuous mathematical landscape to calculate a slope and find a minimum.
So how does SkillOpt handle that?
This is where the text space optimizer comes in. SkillOpt doesn't do traditional backpropagation through the model weights. Instead, it treats the natural language instructions, the actual skill description, as the parameters to be optimized.
Okay, I'm following.
It places the agent in a validation environment, gives it a task, and measures the outcome. Did it write the SQL query correctly? Did it execute efficiently? It computes a loss function based on that real-world performance.
Okay, so it has a performance score. But how does it actually mutate the text?
It uses an optimizer model, which is often another LLM that looks at the loss, looks at the execution trace of exactly where the agent failed, and proposes a targeted revision to the text prompt.
Oh, wow.
Yeah, it iteratively refines the text, testing it over and over the environment, functionally performing a discrete optimization walk through the semantic space of instructions.
So it is systematically finding the optimal configuration of words to minimize the error rate of the target agent.
Yes. It's algorithmically finding the perfect prompt through trial and error, guided by a strict loss function.
And the beauty of this for a developer deploying it is that there is absolutely zero inference overhead.
None at all.
You aren't loading a custom LoRa adapter. You aren't switching out model weights. You just take the highly optimized string of text that SkillOpt spits out and you feed it to your base model. You get the behavioral reliability of fine-tuning with the lightweight flexibility of prompt engineering.
It's the best of both worlds. But, well, the reality of modern software architecture is that a single agent, no matter how well optimized its skills are, rarely works in isolation.
True. We are moving rapidly toward multi-agent systems.
Where you might have a researcher agent gathering data, a coder agent writing the script, and a QA agent reviewing the output.
Which makes the research out of Ant Group and the Hong Kong University of Science and Technology in Guangzhou so timely.
SkillAir.
Yes, SkillMAS, multi-agent system. They are taking the concept of trainable skills and applying it to multi-agent orchestration, turning the interactions themselves into evolvable meta-skills.
And they actually validated this on the newly released DeepSeek V4 Flash model.
Which is impressive. So if SkillOpt optimizes the instructions for a single agent, SkillMA optimizes the social and operational dynamics between agents.
Exactly. When human developers build multi-agent systems right now, they hard-code the workflows.
Right.
They write a script that explicitly says, Agent A, when you finish your summary, pass it to Agent B.
It's a static pipeline.
Yes, and it's super brittle. SkillMAS allows the multi-agent ecosystem to self-evolve its own operational protocols based on experience and environmental feedback.
Oh, that's wild.
The system itself might learn that passing the raw data directly to Agent B produces a lot of errors. But if Agent A first passes it to a summarization tool and then to Agent B, the overall success rate increases.
So it codifies that workflow as a reusable meta skill.
Exactly. The agents are essentially learning how to collaborate, discovering operational efficiencies that a human developer might never have even considered.
This level of autonomous, self-optimizing orchestration sounds incredibly powerful. But, as we zoom out from the research papers to the actual corporate landscape this week, we are seeing massive whiplash.
The contrast is jarring.
The business side of agentic AI is currently experiencing a profound identity crisis regarding these very capabilities.
The strategic maneuvers this week from major tech players speak volumes about the perceived risks of autonomous agents.
So let's lay out the facts impartially. On one side, we have Alibaba and ByteDance. Both of these giants announced simultaneously this week that they are aggressively sunsetting and removing all AI agent features from their respective flagship models, Qwen and Dubao.
Effective July 15.
Right. They are pulling the plug on public, consumer-facing agent deployment.
It is a massive pullback from the prevailing narrative that everyone needs a personal agent in their pocket.
It really is. But on the other side of the aisle, you have Zipu AI leaning in harder than ever. They are pivoting their new GLM 5.2 model to be a dedicated, comprehensive agent tool.
And they are rolling out massive financial promotions to lure developers into building agents on their platform.
And to add another layer of complexity, ByteDance, the same company pulling agents from Dubao, just published a major foundational research paper detailing a new scaling law for agents performing complex real-world tasks.
They are sunsetting the consumer product while publishing the foundational science of how to scale it. It's fascinating.
And the final piece of corporate drama. Alibaba just officially banned its staff from using Claude Code.
They listed it as high-risk software due to internal concerns and allegations regarding Anthropic tracking Chinese users with hidden telemetry code.
So, looking at all these pieces, what is the actual through line here? What is driving this chaotic corporate behavior?
I think it comes down to a fierce, high-stakes realization about security and control. Jane Fraser, the CEO of Citi, actually summarized this perfectly when discussing AI deployment in global banking this week.
What did she say?
She noted that institutions are running two frantic simultaneous races. The first race is to use AI to drive immediate exponential revenue growth.
Obviously.
But the second race is to ensure the ecosystem is utterly impenetrably secure. And right now, public AI agents are failing that second race.
It's the classic tension between moving fast to capture market share and zero-trust security.
Exactly. When you give an AI agent the ability to execute code, search the internet, and orchestrate multi-step workflows, especially utilizing techniques like SkillMAS, where the agents define their own protocols.
You are introducing a massive, unpredictable attack surface.
You are. Alibaba and ByteDance pulling public agents from Qwen and Dubao suggest they've calculated that the current liability, the hallucination risks, and the operational costs of unconstrained consumer agents far outweigh the novelty benefits right now.
They are retreating from the Wild West consumer space to focus on highly controlled, safety-critical enterprise environments.
And Zipu AI is clearly trying to capitalize on that vacuum, betting that they can manage the enterprise risks well enough to capture the developers that Alibaba and ByteDance are abandoning.
But the Alibaba ban on Claude Code is probably the most telling data point here regarding security.
It highlights the extreme sensitivity surrounding agentic workflows. A coding agent isn't just a chatbot. It's a highly privileged user on your corporate network.
Right. It reads your proprietary code base, it can execute terminal commands, it understands your architecture.
If there's even a whisper of a rumor regarding unauthorized telemetry or hidden tracking code, a corporation will instantly sever access.
The industry is rapidly realizing that providing an AI with agency requires absolute, verifiable trust. We are moving decisively toward secure, proprietary, walled garden agent deployments.
Which is the perfect segue to our next major theme, because these highly optimized, reasoning-capable agents are no longer satisfied living purely in digital walled gardens.
No, they are leaving the sandbox. They are being deployed into the physical world, and the implications are staggering.
The transition from digital to physical AI, embodied AI, is where the abstract math of manifolds and memristors meets actual physics.
For years, embodied AI has mostly been the domain of, well, highly produced, billion-dollar robotics videos or extremely constrained single-task factory arms.
The Boston Dynamics parkour videos, basically.
Exactly. But the sources this week show embodied AI hitting the mainstream consumer market in China in a way that feels like science fiction arriving early. You can now hire embodied AI humanoid robots to come into your home and do household chores.
And the price point is the most disruptive part.
It's insane. 74 yuan for 3 hours.
That is roughly $10.
You can rent a humanoid robot to fold your laundry, navigate your messy living room, and wash your dishes for $10.
The economics of that are sparking massive debates right now. I mean, if physical robotic labor is being commoditized at $3 an hour right out of the gate, how do the startups pouring billions into R&D ever achieve a return on investment?
That's a huge question. But looking past the business model, the technological leap required to navigate a novel, chaotic, human home environment is immense.
And a large part of that leap is being driven by a new architectural approach to training these physical models. We saw this in the funding rounds this week.
Guangsheng technology, right?
Yes, an embodied AI startup incubated at Tsinghua University. They just secured hundreds of millions in angel funding.
And their core pitch to investors wasn't just better motors. It was a physics-native embodied AI model, specifically targeting complex automotive manufacturing.
Which is a huge distinction.
So what does physics-native actually mean under the hood?
To understand the breakthrough, look at how robots have traditionally been trained. If you want an arm to pick up a heavy, oddly shaped car door, you train it in a digital simulation like a video game engine.
Right.
The agent tries millions of times in the simulation, learns the visual cues, and then you deploy that brain into the physical robot. The fundamental flaw here is known as the sim-to-real gap.
Because the physics in a video game are just a mathematical approximation. In the real world, the friction on the gripper changes because the ambient humidity in the factory rose 10%.
The servo motors heat up and lose torque.
The overhead lights reflect differently off stamped aluminum than they do off brushed steel. The real world is relentlessly messy and continuous.
And traditional models fail when they encounter that messiness because they only learned empirical visual patterns from the simulation. A physics-native model represents a foundational shift in the latent space architecture.
Okay, how so?
Instead of just mapping pixels to motor torques, the neural network is explicitly architected to inherently predict the fundamental laws of physics, kinematics, dynamics, material stress, momentum.
So it's encoding physics into the loss function and the network topology.
Yes.
So if the robot drops a wrench, it knows how that wrench will bounce and spin, not because it memorized a million video clips of dropping wrenches, but because its latent representation inherently understands gravity, mass, and conservation of momentum.
It learns physics as a native language, not as an afterthought.
That is incredible. And this capability agent's breaking out of chat windows, understanding physical constraints natively, and interacting with complex real-world systems is driving incredible, tangible breakthroughs in deep science.
Which brings us to Alibaba's Demo Academy and their new AI agent, Elements Claw.
This is, without a doubt, one of the most consequential achievements we're covering today. Elements Claw is an agentic workflow deployed in material science. It screened 2.4 million complex crystal structures and successfully discovered 4 previously unknown superconductors.
And the kicker, it accomplished this in just 28 GPU hours.
Let's contextualize that compute time for you, our data science audience. 28 GPU hours is essentially a rounding error in modern machine learning budgets.
People spend more compute time than that running a hyperparameter search on a mid-sized classification model.
Exactly. So how did Elements Cloud do something in 28 hours that typically takes human postdocs years of tedious lab synthesis and requires millions of hours of supercomputer time?
It comes back to the power of the agentic workflow combined with domain-specific heuristic pruning.
Okay, unpack that.
In traditional computational materials discovery, researchers rely heavily on density functional theory, or DFT. DFT is highly accurate, but it requires massive computational resources to simulate the quantum mechanical properties, the electron density of every single atomic arrangement.
It's a brute force approach. You are computationally testing every single piece of hay in a 2.4 million piece haystack to see if it's a needle.
Exactly. But Elements Claw doesn't do that. It acts as an intelligent reasoning orchestrator. Instead of running expensive DFT simulations on all 2.4 million structures, the agent leverages predictive modeling, structural heuristics, and domain-specific knowledge it has been trained on to radically prune the search tree.
So it filters the noise first.
Right. It looks at the massive data set and essentially calculates, based on the elemental composition and lattice geometry, I can mathematically eliminate these 2 million structures as having a near-zero probability of superconducting.
It uses artificial intuition to narrow the field. It refuses to waste compute on dead ends.
It directs the heavy, expensive DFT computational tools only at the most highly promising candidates. It is the practical synthesis of the concepts we've been discussing today.
Yeah, it uses memory abstractions to hold vast amounts of chemical knowledge. It uses reasoning constraints to avoid hallucinating physically impossible crystal structures. And it orchestrates these skills to execute a real-world task.
This is the true democratization of deep science.
You don't need access to a billion-dollar national laboratory or a dedicated supercomputing cluster to discover a novel superconductor anymore. You need a clever, physics-constrained agentic architecture and 28 hours on a rented GPU instance.
The barrier to entry for world-changing scientific discovery just plummeted.
It's inspiring. But, as these agents become more sophisticated, as they begin running our manufacturing floors, discovering novel materials in hours, and navigating our homes, the bottleneck shifts once again.
We've solved the hardware bottleneck, the memory bottleneck, and the reasoning bottleneck.
The final bottleneck in the system is us.
The human element.
How do we communicate human intent to a machine that operates at millisecond speeds, accesses decoupled conceptual memory, and understands physics natively? Which brings us to our final topic. The ultimate interface, brain-to QWERTY.
Currently, our interaction bandwidth is appallingly low.
Right now, we type, which is mechanically agonizing. Or we use voice dictation, which is slightly faster but incredibly imprecise and socially awkward in most environments.
But Meta AI just announced a research breakthrough called brain-to QWERTY. It is a new, documented path to translating human brainwaves directly into text without requiring invasive surgery.
Non-invasive brain-computer interfaces, or BCIs. These have always been the holy grail of human-computer interaction, the ability to simply think and have the machine execute.
Okay, but I know you're going to push back on this.
Oh, I have to step in here with a heavy dose of skepticism. Because as tech enthusiasts, we've been burned by this promise for over a decade. We've seen those clunky, plasticky EEG headsets since the 2010s. You would strap one to your forehead, concentrate until you gave yourself a migraine, and maybe, just maybe, you could make a digital ball float upward on a screen.
It was entirely useless for real semantic communication.
So what makes brain-to QWERTY mathematically or architecturally different from those failed novelty toys?
The skepticism is highly justified. The fundamental physics problem with non-invasive EEG is the human skull.
It's in the way.
It is a massive, thick, biological insulator. By the time the delicate electrical signals from your firing neurons pass through the brain tissue, the cerebrospinal fluid, the bone, and the scalp, the signal-to-noise ratio is just atrocious.
The electrical signals smear and overlap.
It's like standing outside a crowded football stadium and trying to listen to a specific person whispering on the 50-yard line.
So how does Meta's model filter out the roar of the stadium to hear the whisper? Because they obviously haven't made the skull thinner.
No, they haven't changed the hardware of the skull, but they have fundamentally changed the signal processing paradigm using deep representation learning.
Okay.
The old headsets from the 2010s were trying to map raw voltage spikes directly to discrete actions. Spike goes up, ball goes up.
Right.
Brain 2 QWERTY abandons that direct mapping. Instead, it looks for the complex, continuous temporal waveforms of semantic intent.
So it's looking for the shape of the thought, not just a voltage trigger.
Yes. And crucially, it leverages a predictive foundation model, architecturally similar to how an LLM predicts the next word. Meta has been working on this for a while. They previously introduced models like Tri-V2, which were trained specifically on massive data sets of fMRI and EEG data to learn how the human brain processes complex stimuli.
So Brain 2 QWERTY uses a similar underlying architecture.
It takes the incredibly noisy, continuous brainwave data and aligns it with the discrete, highly structured semantic latent space of a language model.
So it's using the context of human language to probabilistically infer what you are trying to say.
Yeah.
If it gets a noisy signal that could be cat or bat, but the previous brainwaves indicated you were thinking about a laser pointer, the foundation model filters out the noise by predicting cat as the most likely semantic intent. It's using the LLM to autocorrect your smeared brainwaves.
That is an excellent way to conceptualize it. It is decoding the signal by leaning heavily on the predictive power of language representations.
And the implications of this working reliably are just staggering. When you remove the mechanical delay of your fingers hitting a keyboard or the vocal cords vibrating, the latency between human thought and agentic execution approaches zero.
You think it, and the agent does it. You achieve a symbiotic state where the cognitive friction between human intent and machine action is effectively dissolved.
We have covered an immense landscape today. We started at the bare metal physics of phase change silicon and ended inside the electrochemical firing of the human brain.
So synthesizing all of this for you, the data scientist who has to go to work on Monday and architect the next generation of models, what does this week actually mean for your daily work?
Yeah, let's tie it all together.
It means that the era of the monolithic, one-size-fits-all transformer where you just dump more data and more compute into a single black box is ending. The future belongs to synergistic, highly optimized modular architectures. The components you were working with are becoming radically more specialized.
Let's give a concrete example of how you might combine these discrete breakthroughs into a single cohesive system next year.
I'd love to.
Imagine you are tasked with building a next-generation, hyper-personalized recommendation engine for a massive interactive platform. Instead of just fine-tuning a massive LLM, you architect an ecosystem.
Right.
You use Mankar's manifold constraints at the core to ensure your reasoning engine stays locked to the topological surface of actual user behavior, guaranteeing it never hallucinates bizarre, invalid preferences.
You give that constrained agent long-term scalable user memory using Memora's decoupled harmonic architecture, so it remembers the abstract evolution of a user's taste over 5 years without blowing up your context window costs.
Exactly. And then you wrap the entire thing in a SkillOpt pipeline, so the system automatically uses a text-based optimizer to evolve its own internal prompts based on real-time user engagement metrics, dynamically improving its own skills without you ever having to manually backpropagate weights.
And eventually, you deploy this entire stack to the edge, running locally, privately, and near instantly on a highly efficient phase-change neuromorphic chip.
It's an entirely new paradigm of software engineering. You aren't just training a model. You are orchestrating an intelligent, self-evolving physical ecosystem.
The data scientists who thrive in the next 5 years will be the ones who understand how to compose these discrete breakthroughs into cohesive systems.
Which leaves us with one final lingering concept to mull over. We talked extensively about how SkillOpt proves we can treat natural language instructions as trainable parameters.
We place the agent in an environment, measure the outcome, calculate a loss function, and let the system optimize the text, prompt itself through discrete gradient descent to achieve a better result.
And we just finished discussing Brain 2 QWERTY, which uses foundation models to filter non-invasive EEG signals, reading your semantic intent directly from your brainwaves.
Those two concepts running in parallel represent a profound intersection.
So here's the provocative thought for you to take away today, building on everything we've explored. If SkillOpt can optimize natural language, and brain-to-QWERTY can read minds, how long until we bypass text entirely in the optimization loop?
Will the next generation of model optimization be driven directly by human subconscious reactions?
Exactly. You're suggesting a zero-shot neural loss function.
The model tunes its own parameters in real time based purely on the brainwave satisfaction or frustration of the user.
Think about it. You sit there, and the agent presents a generated result. Maybe a piece of code, maybe a recommended material structure like Elements Claw. You don't type a correction.
You don't speak.
You don't even formulate a specific semantic sentence in your head. The system simply monitors your continuous EEG data. It detects the precise electrical spike of cognitive friction, the wave of frustration when the code is wrong, or the smooth wave of satisfaction when the output is perfect.
It uses that raw, emotional, cognitive state as the biological loss function.
Yes, it instantly triggers a gradient descent update on its own internal state, dynamically mutating its behavior. No text, no keyboards, no explicit prompts. Just a machine perfectly and continuously molding itself to the microscopic contours of your mind.
Suddenly, that murky diagnostic landscape we talked about at the very beginning.
Yeah.
It's not just the layers of the machine that are hard to distinguish anymore.
The ultimate murky boundary will be the line between the machine and you.
It fundamentally redefines the concept of human-in-the-loop training, stripping away the latency of language entirely.
And that is where the frontier is heading. Thank you for joining us on this deep dive. Keep questioning the architecture, keep exploring the edges of what's possible, and we'll see you next time.